Hi, this is Mr. Precella with my Math 1324 class. Today I want to set up a few word problems, linear programming word problems. And once we've set the problems up, we're not going to go through the simplex method by hand because some of these calculations, the arithmetic gets really messy on these things. The website that I like to use is PHP Simplex, because my math lab won't let you just set it up. They're going to make you punch in the final answers. And so what I'm interested in is you being able to set them up right now. So I'm going to set them up, and then once I've set it up, I'll punch the thing into PHP Simplex, or you may have another program. Do a Google search on simplex method and find yourself another program if you don't like PHP Simplex. But anyway, here's the problem. A company sells sets and kitchen knives. A basic set consists of 4 utility knives and 1 chef's knife. A regular set consists of 2 utility knives, 1 chef's knife, and a slicer. A deluxe set consists of 3 utility knives, 1 chef's knife, and 1 slicer. The profit is $30 on a basic set, $60 on a regular set, and $80 on a deluxe set. The factory has on hand 2,700 utility knives, so they have no more than 2,700. Maybe they won't use all 2,700, but they can't use more than 2,700 utility knives in those gift sets. 900 chef's knives and 300 slicers. If all sets will be sold, how many of each type should be made in order to maximize profit? And what is that maximum profit? Let me do something here. I'm gonna, just bear with me a moment. There, okay, so here we are. I think that's better without all that writing underneath it. And so we have, let's start trying to summarize the information we have in a table. We may not be able to summarize all of it in a table. We'll see some examples where the information doesn't summarize nicely on a table in a little bit. But right now there's basic sets, there are regular sets, and deluxe sets. And the different sets contain utility knives and chef's knives and slicers. And we're also told the profit on each item. When I look at the question, if all sets will be sold, how many of each type should be made? This company has these 3 types of knives on hand, and they're packaging them into sets. So our decision variables would be the number of basic sets, the number of regular sets, and the number of deluxe sets. So I'm going to say that's my quantity. Okay. X1, X2, and X3 will represent the quantity. And then summarizing, basic sets have 4 utility knives and 1 chef's knives, but no slicers. It's just a basic set. You don't need anything fancy in a basic set, like no fancy slicer, I guess. A regular set, 2 utility sets, 2 utility knives, 1 chef knife. The regular set has a slicer. The deluxe set gets 3 utility knives, 1 chef knife, and 1 slicer. That's not that deluxe, I guess. But anyway, now the profit on each set. The profit on a basic set is $30. The profit on a regular set is $60. And the profit on a deluxe set is $80. And the sentence here, the factory has on hand 2,700 utility knives. That means if we total up all the utility knives, used, they cannot exceed 2,700. So that would be less than or equal to 2,700. Now for the knives, What am I going to write down here? I'm not knives, so chef knives. What am I going to write down here? We're told that the factory has on hand 900 chef knives. Do they have to use all of the chef knives? If they could maximize their profit and only use 850 chef knives, is that okay? Yes, so what should go here? Less than or equal to 900. And likewise for the slicers, the same logic, less than or equal to 300. And I think we're ready to start writing out the linear programming problem. So we're going to maximize. P equals. First of all, we're trying to maximize profit. So I'm going to call my objective function P for profit. And that's the profit per set times the number of sets. So 30x1 plus 60 times the number of regular sets plus 80 times the number of deluxe sets. Subject to. Now we need our constraints. How many constraints do you see here? When I look at this table, excluding the non-negativity constraints, I see 3 additional constraints. The first one I'm going to write down is relating to utility knives. Let's see. Each basic set has 4 utility knives for a total of 4 times x1 utility knives used in the basic set. How many utility knives are used in the regular sets? 2 knives per set, x sub 2 sets, so plus 2x sub 2, plus 3 utility knives are being used in each set, multiply it by the number of sets, and that should be less than or equal to 2700. And the chef constraint, 1 times x1, applying the same logic, we get 1 times x1 plus 1 times x2 plus 1 times x sub 3 is less than or equal to 900. And the slicer constraint, well, there are no slicers in the basic sets, but we have 1 times x sub 2 plus 1 times x sub 3 is less than or equal to 300. We also have our non-negativity constraints, but if you're using a program like PHP Simplex, that's already built into the program, okay? So you don't actually enter those non-negativity constraints, but I still like to write them out. So take a moment and look there. Let's see. There. Okay. Take a moment and look at it. At this point, realize I just go over to PHP Simplex and punch in the objective function. Well, I have to tell them how many constraints I have and how many decision variables. I have 3 decision variables and I have 3 constraints. And I'd punch it in. Let's do another one. This one fell out very nicely. Notice they give you the profit per item. I suppose they hadn't given us the profit per item, and they wanted us to calculate the number of units that would maximize profit. Maybe they won't give you the profit per item. They may give you information, okay, here's what they sell for and stuff like that, and you have to determine the profit per item. And that's what's going to happen in the next problem. Where is it? Ah, here it is. Let me put this away. There. Here's the next problem. Let's see. Those of you sitting out there, this is your number 13. Okay, if you're watching this and you're not sitting right here with me, this may not be your number 13 in your homework, okay? But those students that are right here, right now, this is their number 13. A company makes 3 types of candy and packages them in 3 assortments. Assortment 1 contains 4 sour, 4 lemon, and 12 lime candies and sells for $9.40. Assortment 2 contains 4 sour, No, 12 sour, 4 lemon, and 4 lime candies and sells for $7.60. Assortment 3 contains 8 sour, 8 lemon, and 8 lime candies and sells for $11. Manufacturing costs per piece of candy are 20 cents for sour, 25 cents for lemon, and 30 cents for lime. They can make 5,000 sour, 3,800 lemon, and 5,800 lime candies weekly. That's all the candies they can produce. And they're going to take these candies and put them into these 3 different assortments. How many boxes of each type should the company produce each week in order to maximize its profit? And what is the maximum profit? Well, what are our decision variables here? How many boxes of each type of assortment? So the number of assortments they're going to make is will be our decision variable. So I'm going to say let's see, right here I'll put assortment 1, assortment 2, and assortment 3. And we're told that each of these assortments, this isn't that, I guess sour, lemon, and lime candies are good, but when I think of sour and lemon and lime candies, don't you just think of the little hard jawbreaker stuff? It seems sort of steep for assortments of jawbreakers, but I guess that's not we don't need to worry about that. So we're going to have sour candy, we're going to have lemon candy, and we're going to have lime candy. Never mind that lemon and lime are also sour, so there's not much variety in these assortments. Oh, they tell us the selling price. They tell us that assortment 1 contains 4 sour, 4 lemon, and 12 lime candies. And this assortment is going to sell for what I consider this, it seems like it's sort of steep for what you're getting, $9.40. Assortment 2 contains 12 sour, 4 lemon, and 4 lime candies and sells for $7.60. And assortment 3, oh, this is the fancy one. It has 8 sour, 8 lemon, and 8 lime candies and sells for a whopping $11. Surely these are something other than just sell hard jawbreakers, because if so, these figures are astronomical. And before we go on, I never even asked y'all, what should be the decision variables? How many do we need? We need 3 decision variables, yes. One for X sub 1 will be the number of assortment 1s the candy company makes. X sub 2 will be the number of assortment 2. I'm thinking of them as little gift boxes. And X sub 3 assortment will be the number of assortment 3s that are made. So our decision variables are the quantity, the number of each assortments. And we're told that the manufacturing costs per piece of candy are. Well, look at this. They want us to maximize profit, but this is what I was talking about. They're not giving us the profit per item. They've told us, here's what they can sell each assortment for. They're not even telling us how much it costs to make each assortment. We're going to have to figure that out. What they're telling us is that each piece of sour candy costs 20 cents. Each piece of lemon candy costs 25 cents. And each piece of lime candy costs 30 cents. So we're wanting to maximize profit. What does profit equal? Profit is equal to revenue minus cost. So take the selling price, subtract off how much it takes to make those assortments. So we're going to have to calculate the cost of each assortment. I'll say cost of assortment. And once we determine that cost, what are we going to have to do? Here's how much we're selling it for. Here's how much it's costing us to make it. What will we have to do to determine the profit? Okay, I'll let you think of that a moment. Let me get my calculator now. Let's start going through. Let's determine the cost of assortment 1. Each assortment 1 contains 4 pieces of sour candy. So 4 times 20 cents per piece, that's 80 cents. So assortment 1, it's going to cost them 80 cents worth of sour candy, and it's costing them 25 cents for each piece of lemon candy. They're using 4 of them, so that's what, 4 times 25 cents, that's $1. And finally, 30 cents times 12 pieces. I'm getting that it's going to cost them $5.40 to make assortment 1. How much is it going to cost them to make assortment 2? You do the same thing. The number of pieces of candy times the price for each piece. Number of piece times the price. Number of piece times the price. That'll give us, let's see, what are y'all getting? I'm getting $4.60. And finally, the third assortment, the one that's the fancy one, because it's selling for so much, I guess it really depends on what sort of candy you like, the assortment you would like, but it's selling for $11. What did y'all get for the cost of this third assortment? 8 times 20 cents plus 8 times 25 cents plus 8 times 30 cents. I am getting $6. So let's determine, now we can determine the profit per assortment. Profit per assortment. I gotta resist I want to use a 3-letter abbreviation for assortment, and so you see here I had to stick on the little O when it dawned on me what I was using. So here I'll write out assortment. Price minus the cost of each assortment will give us the profit per assortment. So cost them $5.40 to make assortment 1. They're selling it for $9.40, so what have they got left over? They have $4 profit on assortment 1. On assortment 2, the profit is $3, I agree. Here, the profit is, on assortment 3, a whopping $5 per assortment. And I think there's some other information we haven't even addressed yet. What is it? What other information is there? Maybe some totals. We're told that the factory can't make more than 5,000 sour pieces of candy. So if you total up your sour quantities, it can't exceed 5,000. So what inequality should we have there? Less than or equal to 5,000. Lemon can't exceed 3,800. So with that same logic, less than or equal to 3,800. Lime less than or equal to 5,800. And is there any other piece of information up there that I've overlooked? I don't think so. I think I'm ready to start writing the problem. I'm going to push this up now. So I'll say maximize. We're maximizing the profit. That's $4 times x sub 1 plus $3 times x sub 2 plus $5 times x sub 3. That's the total profit on the assortments of that we're selling, subject to, first of all, my sour constraint. That's 4x1 plus 12x2 plus 8x3 is less than or equal to 5,000. My lemon constraint, 4x1 plus 4x2 plus 8x3 is less than or equal to 3,800. And 12x1 plus 4x2 plus 8x sub 3 is less than or equal to 5,800. And x1, x2, and x3 are greater than or equal to 0. And I wouldn't, as I said, these linear programming problems, these word problems can get really messy. So I wouldn't do, I'd use an online program to actually solve them once I have it set up. So, oh, and someone just reminded me I need to make a note. You want phpsimplex.com, but you need to make sure it's in English, okay? -en. I don't remember what language the programmers, what country they were using, the programmers were in, but I know one thing: if you just go to phpsimplex.com, it's not in English, okay? So I think it's in Portuguese, and so put a /en to get it into English, unless you're fluent in Portuguese. Then, any questions there? Well, oh, let's see if I can find another one. Oh, I do. I have another one here. Here I have another problem for that I want to set up. Okay. Customers buy 11 units of regular beer, 9 units of light beer monthly. The brewery decides to produce extra beer beyond that needed to satisfy the customers. The cost per unit of regular beer is $45,000. Well, whatever a unit is, it's something more than what I was thinking, okay? These units, they must be, maybe they're big truckload full, or those big vats they use to make the beer, I don't know. But anyway, it's more than what I was thinking. So customers buy 11 units of regular beer and 9 units of light beer monthly. The brewery decides to produce extra beer beyond that needed to satisfy the customers. The cost per unit of regular beer is $45,000. The cost per unit of light beer is $48,000. So it costs a little bit more to make the light beer. Every unit of regular beer brings in $100,000 in revenue, while every unit of light beer brings in $300,000 of revenue. So the light beer costs more to make, but they're able to sell it for more also. The brewery wants at least $7 million in revenue. At least 24 additional units of beer can be sold. How much of each type should be made so as to minimize total production cost? Let's see. Okay, give me a moment. I'm gonna do something there. I'll pull my old scissor trick, some low-tech technology. I'll pull out those scissors there. That's better. Let's see. So they're producing regular beer and light beer, and what are the decision variables going to be? We don't know how much regular beer they should produce each month, and we don't know how much light beer they should produce. So I'm going to say regular beer and light beer. And so our unknowns, our decision variables would be the number of units of regular beer and the number of units of light beer. I'm going to label them X sub 1 and X sub 2. That's the number of units and okay, from the very beginning I see something. Customers buy 11 units of regular beer and 9 units of light beer. They're going to produce extra beer. This brewery is going to make more than just the 11 and 9 units that they need. They think they can get some new customers. They're going to make more beer than they really need to sell to these new customers. But we know that no matter what they make, they need 11 units of regular beer. So X sub 1 must be greater than or equal to 11. x sub 2 must be greater than or equal to 9. The brewery decides to produce extra beer beyond that needed to satisfy the customers. The cost per unit of regular beer is $45,000. So the cost per unit, let's see, cost per unit, regular beer is costing them $45,000, and light beer is costing them $48,000 to produce. Every unit of regular beer brings in, okay, here's the revenue. Okay. Revenue. The revenue, it brings in $100,000 in revenue, and light beer $300,000. I'll put those with dollar signs there. Same thing there. The company wants at least $7 million in revenue. So if you total that revenue column, they want at least $7 million. So what inequality is implied by that phrase, at least $7 million? Greater than or equal to $7 million. I'll make sure I got the right number of zeros there. 3, yes, okay, there's $7 million. And so far we haven't addressed the fact that the brewery wants to make extra beer. So at least 24 additional units of beer can be sold. So they're gonna have to make at least 24 additional units of beer. So that's interesting. How many units of beer do they need total? Here's my scratch work. I'm thinking to myself, they need at least 24 additional units, but they're also having to make at least 11 units of regular beer and 9 units of light beer. That's 20 additional units. That's 20 units there that they make automatically. So mentally, I conclude that they need 44 addition. They need to make at least 44 units of beer. So if I total x1 and x2, x1 plus x2 is not going to be greater than or equal to 24. They need 24 additional units over the 20 that they have to make. This stuff is already sold here. The 11 and 9 are sold to their old customers. So they're making 20 here and an additional 24. So that's going to be greater than or equal to 44. Any questions on my logic there? And normally it seems like the last column is always the column we use for our objective function. That's the last piece of information they usually give us, but is that the case here? No, that's not the case here. No, not maximize. We are minimizing. We want to minimize the cost of production. Minimize the cost. We use the cost column, 45,000 times the number of units of regular beer plus 48,000 times the number of units of light beer, subject to and let's see, I see several constraints. I see that if we take x1 plus x2, that has to be greater than or equal to 44. I also see that x1 has to be greater than or equal to 11. That x sub 2 has to be greater than or equal to 9. These two inequalities here are taking care of the non-negativity constraint. If x is greater than or equal to 11, it's certainly greater than or equal to 0. So x1 and x2, so greater than or equal to 11 and greater than or equal to 9, that's taking care of the non-negativity constraints. Do we have any other constraints? Yeah, there's another constraint, that revenue constraint. Each unit of regular beer brings in $100,000 of revenue, so 100,000 x1 plus 300,000. X2 has to be greater than or equal to 7 million. And as I said, we have the non-negativity constraints. I'll write them down just because it's my habit to always write them down at the end, but these two constraints here already take care of those. Now, if you're going to punch it into a program, remember, you're going to have to, an online program, a simplex program, rather than doing it by hand, and that's what I encourage you to do here. You're going to have to, what's the x sub 2 coefficient here? 0. For this one here, what would be the x sub 1 coefficient? A 0 as well. You could go through and divide through by 100,000 right here, so you would only have 1x1 plus 3x2 is greater than or equal to, you'd lose 5 of those zeros, so what would that be, 70? If you don't want to type in all the zeros, but either way, here's the setup. Notice the information wasn't given to us in such a nice, orderly fashion. We were still able to summarize it in a table, but it wasn't so organized where the last column's automatically the column used for your objective function. They didn't just say, oh, here's the minimum amount they need to produce. We had to calculate the minimum amount to be 44. So the information isn't given quite as nicely, but we're still able to set it up as a pretty nice linear programming problem. And I have one more I want to do. Okay, let me find it. Okay. And let me, okay. Pull out my old scissors, which you can't see me doing there. Okay. And as part of a weight reduction program, a man designs a monthly exercise program consisting of bicycling, jogging, and swimming. He would like to exercise at most 24 hours, devote at most 6 hours to swimming, and jog for no more than the total number of hours bicycling and swimming. Gosh, he has a lot of restrictions. I think he's not really into this exercise program if he's putting all these restrictions on it. Let me reread it. He'd like to exercise at most 24 hours. So he doesn't want to exercise more than 24 hours in is it a week or a month or what? Let's see. Month? Oh, so he doesn't want to exercise more than 24 hours in a month. Devote at most 6 hours to swimming, and swim and jog for no more than the total number of hours biking and swimming. The calories burned per hour by bicycling, jogging, and swimming are 200, 617, and 293. Oh, wait a minute. I thought we were always told that swimming burned more calories than jogging. Look at that. Jogging's burning 617 calories and swimming's burning 292 calories. I don't know about that. How many hours should be allotted to each activity to maximize the number of calories burned? So he's trying to maximize the number of calories he's burning, subject to the restrictions he's set up of what he wants to do and stuff like that. So there are 3 activities. What are our decision variables? Our decision variables, how long is he going to spend bicycling? How long will he spend jogging? How long will he spend swimming? So I'm going to say bike, jog, and swim. And the decision variables are the number of hours, x1, x2, x3. That's a pound sign for number of hours. That is not a hashtag. That is just a pound sign for number of hours. And let's see. He would like to exercise at most 24 hours. Okay, I see a constraint. If we total all the hours he spends exercising, he wants it to be at most 24. At most means what inequality? It means less than or equal to 24. He doesn't want to spend more than 24 hours exercising during the month. And he wants to devote at most 6 hours to swimming. So he's spending X of 3 hours swimming. That can be at most 6. So that has to be less than or equal to 6. And he wants to jog for no more than the total number of hours bicycling and swimming. Okay, I don't know how to summarize that on this table. Sometimes you run into information that can't be summarized nicely on a table. So I'm going to write it down and take it apart. He wants to jog for no more than the total number of hours biking and swimming. I'll say total of bike and swim. So let's try to translate that. The number of hours he's spending jogging is X sub 2. He wants X sub 2 to be no more than means less than or equal to, right? The total of biking and swimming. While he's spending X sub 1 hours bicycling, he's spending X sub 3 hours swimming, so that total would be X sub 1 plus X sub 3. Any questions there? No, we're not through with the problem, I know. Just sometimes you run into information that you can't really translate nicely using a table. So here I just had to write that phrase out and translate it algebraically. Now calories. The calories burned per hour. This is the ludicrous part. The number of calories. So 200 calories bicycling, 617 swimming, and 617 jogging, 293 swimming. I think that should be more, okay? So any kinesiology majors out there? No? Oh, well, I guess this is for business. Okay, so, but anyway, hopefully, well, we don't have to worry, okay? Even if these numbers seem a little bizarre from what we know, that's fine. That doesn't impact us. This isn't really us doing the little exercise program. So we want to maximize the number of calories. By the way, if you look, I think I've gone through every piece there. So we're going to maximize. And what do I want to call my objective function? I guess I could use a Z, but I think I'll use a C for calories. I'm trying to maximize the number of calories burned. So 200 times the number of hours for biking, 617 times the number of jogging hours, plus 293 times the number of swimming hours, subject to well, one constraint I see very quickly is that if you total the decision variables, they got to be less than or equal to 24. So X sub 1 plus X sub 2 plus X sub 3 must be less than or equal to 24. I see another constraint. X sub 3 has to be less than or equal to 6. So X sub 3 is less than or equal to 6. And is there another constraint? Yeah, the one that's not in the table right here. I'm going to take this constraint. I'm going to move it down here. I'm going to write it here. But I'm going to align my like terms. So X sub 1 and X sub 3, I'm going to move over to the left. So that'll become a negative X sub 1 plus X sub 2 minus X sub 3 is less than or equal to, what have I got here? Okay, I have 0 left. I moved the X sub 1 over. That became the negative X sub 1. There's my arrowhead. That's not a very good arrowhead, is it? There, well, okay. So a negative X sub 1 plus X sub 2 minus X sub 3 is less than or equal to 0. And remember, for the omitted terms, when you're punching it into phpsimplex.com/en, those omitted terms will have coefficients of 0 for the second constraint for x sub 1 and x sub 2. And even though we don't punch that into the program, I like to write out my non-negativity constraints. So sometimes you'll be given information that, I always say, summarize the information in a table to the extent that it's possible to do so. This piece here, I'm not really sure how you could have summarized it nicely in a table, but we still were able to, we had to resort to just translating the statement algebraically, but it still fell out pretty nicely. There are my constraints. There's my objective function. If I asked you which one of those was the objective function, you should know that this thing here, the thing that's being maximized or minimized, is the objective function. These inequalities, those are the constraints. So you should know that terminology. And any questions? Hopefully this has helped you get a better hang of translating these word problems into systems, linear programming problems. And I'm going to take a break before my next class. Okay? Bye-bye.